Welcome back to the Biomechanics 1 video series. This one's looking specifically at concepts of balance and stability. We'll divide this into two components or two videos. One is the introduction of balance and stability and what it entails and why we try and investigate it and what its importance is. And in the second video we will unpack the variables that tend to affect balance and stability. So there's two components in balance and stability that are really important. One is the whole concept of equilibrium. In other words, for a person to remain in the position that they are in, or a body to remain in the position that it is in, it needs to have a state of equilibrium. And what are the factors that tend to affect that? Because this will impact balance and stability. Okay. The other is the concepts of torque, which we've unpacked in previous videos. But these two are kind of essential to the understandings of balance and stability. It has lots of applications in biomechanics. So, for example, if you are a swimmer and you want to launch yourself from the starting blocks, you want to be on the very edge of stability because you would want to exert very little force in order to initiate movement, right? You want to propel yourself forward as fast as possible. So the balance and stability that you are experiencing is going to be on the very edge of instability. And how do you maintain that and how do you maximize that? Same thing is true for a sprinter. So a sprinter would also want to be on the very edge of instability or the very edge of stability in order to initiate a condition of instability, in order to propel themselves forward as fast as possible, right? If their goal is to be as quick as possible out of the starting blocks, they need to do that with minimal force in order to maximize forward acceleration. Same thing here. If you're looking at basketball, you have two different players with their bodies in different positions. This player over here, the defensive player, would have instability going backwards, meaning it'll take very little force to displace him backwards. But that's good for him because he can then propel his body backwards very, very easily in order to initiate the defense. The attacking player, for example, will also have some instability going forward, but that allows him to propel himself forward in either direction a lot more quickly or rapidly. So stability plays a key factor in many different types of situations. And some we want to maximize stability, and in others we want to minimize stability. So what do we need to understand around this whole concept of balance and stability, and where does equilibrium and torque feature in all of this? Okay. So, to explain that, we're going to start off fairly simple. So, let's say, for example, we have a block resting on a table and it's kind of pinned on one edge. So, there's a couple of forces acting on this block. So, remember, this block will have a center of mass, and we've spoken about this at length before. And the forces acting on the center of mass, we know is the force of gravity, and that's pulling it downwards. But since it's resting on a table, there's also the normal force, which is perpendicular to the surface and tends to counteract the gravitational force, right? It'll be equal and opposite, so this is the force normal. And for an equilibrium situation to be true, the net of these forces equals 0. And we've spoken about that before as well. So it basically means that the sum of all forces, and in this particular situation it's all the vertical forces or the forces in the y-plane, equal 0, right? They cancel each other out, and hence the block doesn't move up and it doesn't move down. There's also no forces acting in the x direction, so I'm not noting these explicitly since there are no forces being applied. It is assumed that all the forces in the x direction also sum up to 0. Okay. So that's the first thing for equilibrium to be true. When we talk about balance and stability, there are a few other things that would affect how stable this particular object is when it is resting on this particular surface. One is the fact that there is a base of support. So basically the length of this particular box will also affect how easy it is to displace. We'll call this the base of support. That's going to be an important factor. So you could relate that to something being tall and very narrow, would have a small base of support. If something is wider, it has a wide base of support. Okay, so base of support is a critical factor. The actual mass of this particular object. So if we call this principle 1, then the second one would be the actual mass of the object. So the heavier something is, the more inertia it typically has, and the more difficult it is to displace or to get into an unstable position. Its height, or the height of the center of mass, right, relative to the surface on which it tends to stand. So if this was higher, it'll be easier to displace, and I'll show you why that is the case in a second. And the last one is the distance of the line of the center of mass relative to the base of support. Okay, so how far is this center of mass from the actual edges of the base of the support? Base of support. Okay, great. So that's kind of like equilibrium, or the concepts of equilibrium taken care of, right? We want this to be relatively stable. The forces in the vertical direction balance out. The forces in the x direction tend to balance out. Sum of forces tends to equal to 0. There's another condition of equilibrium that has to be met for something to have stability, and that is that the sum of all moments must also equal to 0. That's where the concept of torques comes into place. Okay, so what does that even mean? So what you will notice is that, say for example, this force of gravity was acting down, and I completely removed this table, but it is still pinned around this bottom left hand corner. You will notice that since there's a downward force acting on this block, it will tend to cause this block to rotate in a clockwise direction, right? So if I remove this table, there's no normal force acting on this, so the only force acting on it is this force of gravity, and if I pin it around here, this block will tend to rotate in a clockwise direction, which means that there's a torque acting, right? So remember that a torque is defined as the force that is applied multiplied by the distance that the force is from the axis of rotation. But remember, it's not just any distance, it's the perpendicular distance, right? So if I have this force, what is the perpendicular of this force to this axis of rotation? Well, if I can just kind of extend this down, then the perpendicular distance is over here, right? That is the distance that the force is acting from this axis of rotation, so that would be your R component. Okay, so I have this force times the distance would create a torque, a clockwise torque, a torque force in the clockwise direction. Good. But if this table is present, notice that there is a normal force, and this normal force will create an anti-clockwise rotation, right? So since this force is acting upwards and it's still pinned, technically speaking, around this bottom left hand corner, then the torque force by the normal force is equal to the force normal multiplied by the distance that it is from the axis of rotation, right? Which is this same R value, right? It's the perpendicular distance of this force being applied from the axis of rotation. And you'll notice that these are then equal and opposite, and therefore the sum of all moments will equal 0. Alright, so hopefully that's made some intuitive sense. So this is all the forces in the y direction equaling 0, and all the moments about this particular point here also equaling 0. Good. Okay, so if that all makes sense, then I will introduce another external force. Let me just try and get a slightly different color here. Let's say, for example, I apply a force at the top over here. So this is the force of me pushing, right? Now this will create a turning force as well, a torque. Remember that the force is not acting through the center of mass, so there will be rotation that tends to happen. So if we just look at the rotational component, what is the torque created by my pushing force? Well, it is the force of the push multiplied by the distance, the perpendicular distance of the force to the axis of rotation. So again, if I kind of just project this further along the line of action, what's the perpendicular distance between the force and the axis of rotation? Well, this would be my new r. So this is the r of the push, right? That's the distance from the force to the axis of rotation. Okay, so that's the torque that would create. So in essence, what this would cause is this whole block to pivot around this fulcrum and in essence reach this new position over here, right? If I just keep the force there, it's going to stay in this particular position. But what I'm interested in is what would happen the moment that I remove this force. So remember, the force is being still applied at the top here. So the instant that I remove that force, would this block continue to tipple over, or would this block return to its initial position? That's the question. Okay, so let's try and investigate that a little bit more. So if this is the block in its new position, remember that there's still its center of mass, and the center of mass is acting straight down. There's a force of gravity acting on that center of mass, and that is acting straight down. Remember that I still have that pivot point over here, and that in essence means that there is a torque that is going to be acting on this particular system. Remember that this force is just going to be acting straight down. So if I want to calculate what kind of a torque I have, and this is the torque being created by gravity acting on the center of mass, it's the perpendicular distance between the force application and where the fulcrum is. Remember, that's r. Okay, so it's still this force of gravity acting on the center of mass multiplied by the distance that it is from the axis of rotation. Notice that this would cause a clockwise rotation, so that would force this block to move back to its initial position, right? In other words, it's going to be moving back to this position where it all started. Okay, why would it stop there? Well, once it's in this position again, remember there's a normal force acting on it, and the normal force creates a torque. The force of gravity is in this position again, and it creates a counter torque, and there will be no net rotations. Alright, so since here this object is in the air, the table's down here, there's no normal force acting on this object anymore, and it would be free to rotate until it reaches a new equilibrium position. Alright, so hopefully that all makes sense. So I'll just say here, therefore causes a clockwise rotation if the force that I was applying up here is removed. Okay. What happens if I were to continue to apply that force, and all of a sudden this particular block finds itself in a new position where it is out here in this position over here, right? If I removed the force that I was applying in order to initiate this rotation, would this block continue to topple over, or would it return back to its initial position? Okay, so if I had to investigate that now, remember that the center of mass of the block would have moved. Force of gravity is still acting through this center of mass. So Fg is over here. My fulcrum, the point around which it pivots, is over here. So again, if I just had to project this force downwards, Remember, R is going to be the distance between force application and the axis of rotation, so my new R is over here. So again, it would create a torque, which is the force of gravity times the distance that the force is acting relative to the axis of rotation. However, note now that this gravitational force is to the right of this fulcrum. That means I would initiate a counterclockwise rotation. So this is counterclockwise, right? So when this force is removed, this particular block would just continue to topple over in a counterclockwise rotation, meaning that it would reach a new equilibrium position on this side. It would not return to its initial equilibrium position from where it started its rotation. Okay, so hopefully that's kind of made sense. So we have this scenario over here where there are a couple of factors that are affected, or different types of equilibrium that I have to be aware of, right? One is called stable equilibrium, which is the first scenario that we saw. If I apply this force, provided that the center of mass is still within this base of support here from where it started, this object will tend to return to its initial position when this external force is removed, right? So stable equilibrium is when an object returns to its initial equilibrium position. Unstable equilibrium is when the force was applied, and in essence what tends to happen then is now all of a sudden this force of gravity is outside of this initial base of support, right? So if this was the base of support over here where we started off on, this is now falling beyond those limits and therefore creates an unstable equilibrium position, meaning that this object will seek a new stable equilibrium position. It will not return to its initial equilibrium position. And then third and final, there is something called neutral equilibrium, meaning that an object is not seeking its original stable equilibrium, but it's not also reaching an unstable equilibrium position. And an example of that would be, say for example, a ball that is resting on a particular surface. So yes, there's a downwards force on it, and there's a normal force acting upwards on it as well. So it is in an equilibrium position. If I were to apply an external force and this ball would roll to a new position, if it rolls over here, its center of mass is still within its base of support and there's still a normal force acting on it. So even when it has been displaced, it is still in a stable position, but it is not in its initial position anymore. So it's a combination basically of the stable and unstable. In essence, it remains neutral the entire time. Doesn't matter how far that ball tends to roll. Alright, so three different types of equilibrium, all affected by the center of mass, the base of support, the mass of the entire object itself, its height, and the distance that the line is relative to the base of support. I will talk about these factors in the next video. Hopefully this introduction has made sense, and I'll see you guys on the other side.